We are live. We will be going live for answering questions here in about 5 minutes. I just wanted to make sure that we got the live stream up and running.
This kid size.
Dude, that's probably one of my favorite shows.
It's that in the office for me.
Oh, I know. Is there a shape one of them? Absolutely.
Back to your copy. Sully with
Absolutely
the
not,
show.
sir. There's not. Well, we're good.
No. There's a big lag. There's nothing. Oh, okay, yeah. Is it live?
Yeah.
What's up? Anybody watching?
I'd love so hard to.
Michael Beachville said hi. Oh, there's one person watching.
What's some advice you
I don't
give
know.
to the younger
I don't think you can tell.
Huh?
I don't think you'll be able to tell unless you see their username. If they have one.
Yeah. It's really weird because it's like 10 seconds behind.
Yeah.
Wait, ready?
10 seconds?
Hold on. That's so far behind that. 1, 2, 3. 3 seconds. 3 seconds. That's pretty. Look at that face. Oh! Okay. I'm right gonna find a skate. Oh, what?
Jaden might have one.
There's so many people in here. That was loud.
It was, I mean, it wasn't bad. We just don't, just remember we have a quiz on Friday for you.
I know.
Do we do an experiment this week?
No, we just really like review everything that we did last week, all the inoculations. For our class, I know she did an extra one, so literally on Thursday when we come in, like all I have to do is take the quiz. We did what we had to do on Thursday too.
Huh.
So we come in, take the 5-minute quiz, and we hire you.
Wow.
I am high. So high. Yeah, dude.
I'm spending 4 hours studying this tonight. This study guide is pretty extensive. Compared to the other ones. Like 0 to 6 little points.
Is that the one for?
This is for.
Oh, here. Okay. I was like, what's the actual one? But yeah.
I know, right? Alright. Did you go run?
Yeah.
How was it? 3 months.
Guess what, folks? It's actually working.
Is
Yeah,
it?
no.
Yeah, they're messing up.
Hey, there's a little bit of a lag. There's a 3-second lag.
Oh yeah, yeah. There's always a lag, but it's broadcast. I'll take 10. That's let's see, we're up to number 3, so that's good. Where's that back home? Okay. Do we have any friends coming that we know of other than this?
I thought my friend Josie and Kate were supposed to come, but
They might show up here in a little bit.
yeah, okay. I mean, don't wait for them. Like
They're not real
sucks to suck. Sucks to suck.
Don't wait for it. Okay. Okay, so those of you that are online, feel free to ask questions. I can see the chat bar. If we want to talk about questions, I'll try to answer them during the live stream. Okay, so welcome to the study session. How are we doing?
You're pretty great.
Pretty great. Awesome. So, what questions do we have?
I don't know. I feel like this test is going to be like worded differently than like the last couple ones. Like
The content's just...
yeah, the content's a lot different. I feel like. So I was like, could you give us like an example of like? Or, I would say like, never mind. I was gonna say like an example of a
go ahead and ask
question.
me.
I was gonna say like an example of like a more in-depth question. So I feel like these questions are like a lot more, could be more in-depth than the last couple.
Okay, so I guess a question could be something like during virion release from a cell, if the cell were to explode, this would be an example of what? Yeah, the answer is lysis, because lysis causes cells to explode. A question that I could ask you is, what are the steps in order of the cell replication cycle, or viral replication cycle? Do you want to know those in order? I could ask you a question like, the genomic content of viruses is predominantly what? I could ask something like DNA, mRNA, tRNA, rRNA. None of the above. None of the answer. Or on that question, it would have to be something like A and B or B and C, because it's either going to be DNA or RNA, specifically mRNA. Like, what are you worried about, I guess?
I don't
Something
know.
More specifically that you're...
Let me look through and I'll ask some more questions. I'll let somebody else get in.
I'd like to go over penetration and coding. Like, that concept to me just doesn't look quite good, I guess.
Alright, penetration and uncoding.
Just like the slide right here. Where like
Okay, so the question was, how does penetration and uncoding happen when comparing a enveloped virus versus a naked virus, correct?
Yeah.
Alright, so that's a question that we want to answer. So let's start off with so on top here you have a enveloped virus. On the bottom you have a naked virus. The enveloped virus is going to interact with this host cell membrane because it's surrounded by host cell membrane itself. The envelope is a phospholipid bilayer with glycoproteins distributed throughout. Does that make sense? Now because of this, because we have the membrane surrounding, and I can make it a double membrane, surrounding that nucleocapsid, they actually merge. Okay? So when you get unpacking happening here, what's going to happen is these two, let's draw an arrow over here. It's through certain protein-protein interactions that we're not going to go into detail of. The envelope merges with the host cell membrane. Okay, so this membrane surrounding the envelope, surrounding the virion, actually merges with that host cell membrane. They become one. So in the end, you have a slightly bigger or longer host cell membrane with a nucleocapsid inside of it. That nucleocapsid, once it's in the cytoplasm, there are proteins that tell it you're in the cytoplasm, and it causes the nucleocapsid to disassociate or fall apart. the alternative to an enveloped virus getting into the cell is if it's a naked virus. The naked virus is going to have those glycoproteins or the spikes. Instead of being in the host cell membrane, those glycoproteins are actually right on the surface of the nucleocapsid itself. And if you were to zoom in, you're going to have host cell receptors that are going to interact with those glycoproteins. Okay? And that interaction is going to cause a process called endocytosis to occur. So in endocytosis, what happens, and I'll just draw like this, is this nucleocapsid. It's very similar to phagocytosis, except it's for smaller targets. It's going to eat or internalize the virion itself. Okay? The difference is in the end, you are going to end up with a virion surrounded by an endosome. Okay? This endosome, so in normal endocytosis, a cell internalizes something, and then you have the endosome fuse with a lysosome. This endolysosomal fusion causes the pH to drop. Alright, in naked viruses, when the pH drops, it causes viral proteins to disassociate from the nucleocapsid, and they actually punch holes or channels into the virion. Alright, or into the, not the virion, I'm sorry, they misspoke. They punch holes into the endosome, causing it to more or less dissolve. At which point, you just have that naked virion inside of the cytoplasm, which is hanging out in the cytoplasm. And just like in the enveloped virus, once that gets into the cytoplasm, it causes the nucleocapsid to disassociate or dissolve, releasing the genome, either the DNA or RNA, into the cytoplasm. It's just a generic of how those two differences work. Does that make sense? Okay. We have a question. We actually have my wife saying that my son says hi. Hi, Matthew. They put him up on my TV. Oh, you can watch me. All right. So does that help answer that? Does that clarify those two differences? Very good. All right. What other questions do we have?
So when the virus, when it gets endocytosis in the endosome,
Yeah, when it's endocytosed, that vesicle that takes it up is called an endosome. You've probably heard of like phagocytosis before, when we talk about white blood cells. Endocytosis is the same process. It's just how big of an object is the cell trying to take in? Is it trying to take in this piece of chalk, or is it trying to take in a bowling ball? Okay. The size will determine if you call it endocytosis or phagocytosis, but they're going to be very similar processes once it's inside of that cell. Yes, the pH dropping is what causes those viral proteins to dissolve in the endosomes. They literally disassociate from the surface of the nucleocapsid and punch holes or channels into that endosome, releasing the nucleocapsid. Good. Yeah, virology is a little tricky, but at the end, I want you to remember that viruses are genetic programs. Right? They're not alive. They're not dead. They're either active or inactive. You know, it's really important. One of the best or most fun things, in my opinion, to do is that when you think about viruses, really think about it as the virus is a program. And that program wants to get into a specific cell, and it wants to make copies of itself. That's what it's trying to do. Viruses are merely a genetic program. It's like if I were to give your computer, if I installed a new program on it, like Windows, Word, like Microsoft Word. If I install Microsoft Word on it, that is just a program that runs, right? And you can type. A virus is the same way. It gets into a cell and it just runs the genetic program. There's just a genetic program in that DNA or in that RNA that is just trying to make copies of itself. Good, sure, okay. Any other questions, Jack? What do you have?
How are viruses classified? Did you just want like family, genus, species, or did you want like?
Yeah, well, the whole point of that conversation was that we had a slide on classification where, you before 1973, it was plant, animal, viruses, and bacteria. After 1973 is when we went to our classification system. And again, I want you to remember that Viridae, whenever you see Viridae, that's referring to families of viruses. So Pox Viridae is not a virus. Pox Viridae is a family of pox viruses. Okay? Whenever you see something italicized, that means that it is part of the genus. All right, and then the species is always in English when you're talking about viruses. I just want you to have a general idea of how they are classified, because it's changed since the 70s. Sometimes you'll be working with older clinicians, and they won't appreciate those differences. And like I said in class, the news always messes it up. They'll talk about families all the time. They'll say, "Oh, this is the Pox Viridae virus," and it just drives you up the wall because it's like, no, it's not a virus; it's a family of viruses. Do we have any questions online? No. Okay. What else do we got? Good questions so far. I know you've only had a few hours to look at this study yet. Again, with the cheerleaders going to nationals, I wanted to make sure we all had as much time as we could.
This is the last place I thought was completed.
Yeah, right before the construction wall. What other questions do we have? And they can be general questions too. Is there anything in these 3 chapters that didn't make sense? Is there a concept that we went over that you look at it and you're still scratching your head? Yes, please.
The cephalosporins and like antibiotics.
Yes.
Just like you said something about how they're similar to penicillin and they inhibit bacterial enzymes from producing cell walls. Is that what the antibiotic does?
Yeah, good question. All right, and so if you were to draw a penicillin versus a cephalosporin, it's very easy chemically. Like if you're just looking at it chemically, it's very easy to see that they're very, very close, right? And that's because they're related. Their mode of action is very, very similar to one another. So like a penicillin and a cephalosporin, both of them are going to be focused on inhibiting cell wall synthesis. And the example that we go over in class is the synthesis of peptidoglycan. Right? Peptidoglycan synthesis is, some of you haven't had this yet, but we go over this tomorrow. But there's those proteins that are called NAGs and NAMs. They're alternating proteins that make up these layers. I call them chain link fences, like sideways. And these, basically what's happening is when you're taking an antibiotic, what you're trying to do is you're trying to block the function of a bacterial enzyme. Okay, so these will block the function of bacterial enzymes. And the classic example I like to use in class is like with the square-shaped covering the bottom cup. But they are going to act in a very similar fashion. Anytime that you block cell wall synthesis, we're talking about stuff like peptidoglycan, you make the bacteria very, very, very sensitive to osmotic pressure. So if you go from like your throat to the stomach, or you change different places in the body, there's just naturally different concentrations of salts in those different microenvironments. Changes in osmotic pressure are going to lead to lysis of the cell wall. And almost all bacteria will not survive if they cannot synthesize peptidoglycan. It's a lethal thing to not be able to synthesize peptidoglycan. Does that help answer your question?
Yeah.
Okay.
What is the difference between a nucleocapsid and a viron?
Oh, very good. All right, so the nucleocapsid. So if I were to just draw a basic virus up here, let's just say that, right? Let's say that's a virus. The nucleocapsid is the shell, all right? When you talk about a virion is everything. It's the genome inside, the DNA or RNA, the capsid, the glycoproteins. A virion is a fully assembled, fully infectious viral particle. The nucleocapsid is just the shell on the outside that protects the genome. That's it. Now, when you remember when we talked about capsids, if you were to, take this drawing and break it down, each one of these capsids is made up of capsimers. What were capsimers? They were small subunits of proteins. So, for example, if this was an icosahedral capsid or a triangle-based capsid, you'd have a bunch of these small individual proteins forming a triangle. Right? Each one of these individual little circles is a capsimer that form into these triangles that form the capsid surrounding a virion. But a virion is a very specific term. That means a fully assembled, fully infectious virus particle. Okay? Does that help clarify that? Capsimers.
Capsimers that just create flowers.
Yeah, those are protein subunits, small little subunits that create. Think of capsimers as the Lego blocks, and the capsid is like the castle that's surrounding the little Lego guys. I'm trying to come up with something that's more representative. Good. All right. What are you most concerned about? Because we're spending a lot of time on viruses. Is there anything about it that doesn't make sense? Reality, you have a core of some type, a genome, DNA or RNA, never both. And then you have some type of a covering around it, whether that's the capsid, whether that's an envelope, whether that's a combination of the two. You have a core and a covering, and you're going to go through the steps of replication. Ultimately, you're going to lead to the virus reproducing in a cell. The key word is in a cell. Viruses have to be inside of a cell. They're obligate intracellular parasites. They have to be within a cell in order to be infectious, or in order to replicate. It's a common misconception that the public has. Is they think that viruses are just on surfaces dividing and taking over. They're not. They can't. Most viruses cannot survive outside of the body for more than 15 minutes. Good. Yes.
Okay. This is a different topic, but
Okay. That's good.
I was reading through my notes, and disinfection and decontamination, they sounded kind of like parallel on some components, like the physically removing debris or like bacteria.
Yeah, so we read go to disinfection and read the last line on that.
So to destroy vegetative pathogens, but not bacterial spores.
Yes, so that's a huge key right there. When you're disinfecting something, you are destroying any bacterial cell, like living bacterial cell, but any spores that are on the surface are still there. So you can say, oh, I disinfected that surface, that inanimate surface or whatever. But any spores that are there are still there. Okay, now go to the decontamination slide.
Removes microbes and debris.
Yeah, microbes and debris, and what was the other part of the slide?
Reduces contamination to safe levels.
Yeah, so reduces contamination to safe levels. Safe levels doesn't mean that you've removed all of the vegetative cells. That just means that you've decreased the amount of, let's say you had 10,000 bacteria on the surface. Maybe now you only have 5. Okay, so it's not that you've destroyed all vegetative cells on that surface, that you've taken it down to a safe or acceptable level. Does that make sense?
Yeah.
So they are close. They are very, very close.
As far as like bacterial endospores go, is there any of these like 5 different types that like we need to focus on?
Of cleaning?
Yeah.
Well, whenever you're talking about spores, it's real like sterilization kills spores. If you run something through an autoclave, you will kill the spore. The other main thing that will kill the spore is a sporocidal agent, right? Something that literally will dissolve it away. A sporicide either breaks open or dissolves the cortex of the spore. But anything else, like heat alone, generally speaking, will not kill most spores. A little bit of pressure won't. Most chemicals won't. It's the combination of heat and pressure, which is what the autoclave does, that can kill the spore. Or you have a special chemical that dissolves that cortex away. So if you're specifically talking about spores, you have to have the correct cleaning agent around. And that's why we talked about using a sporicide in doing that cleaning.
So like using a sporicide, like physically removing that, would that be a type of decontamination? Or type of disinfectant, sorry?
Would using a sporicide be a type of disinfection?
I think that's where I kind of tripped myself up.
Yeah.
Because I was trying to
You're going down the rabbit hole.
Yeah. Since we're there, would it be more?
I really would give decontamination
That's what I
because you're not telling you're going to kill the spores.
You're gonna. At that point, you'd be consider that more of a decontamination because you're removing something to save levels. Right? You've brought it down enough. But yeah, that's a little bit more detailed about what I'm going to look for.
Okay.
Yes, yeah, I do want you to know the differences between critical, semi-critical, and non-critical devices. And we went over examples of each in class. You remember what those were? So if we say something like a critical medical device, what's so? Yeah, surgical suites. Things that are going into sterile sites of the body, surgical instruments and such. If we are talking about semi-critical medical devices, the example we gave there was nasal cannulas, trach tubes. These are things that are coming in contact with the mucosal membrane. The non-critical medical devices were the stuff on the surface, like tape, IV lines, stuff that's not going into the body, that's just sitting on the surface. All right, and all of this is managing risk of infection of your patient. All right, and each one will require a different level of sterilization. Good. Yeah, this chapter, like I said, that the decontamination, disinfection chapter, whatever you want to call it, microbial control chapter, is a little frustrating because a lot of the terms are close. But I do want you to appreciate that they mean different things, because I promise when you get to the clinical setting, you're going to hear people misuse them all the time. And if you're the one misusing the term, and somebody that knows what they're talking about hears it, they're going to assume that you're naive or that you don't know what you're talking about. And I don't want them to think that. I want them to look at you and go, wow, you actually know what sterilization means. You actually know what disinfection means. I want you in the surgical suite with me. I don't want the person that's, from some other school down the road that keeps saying that everything's sterile, because they're going to contaminate my surgical field, and I don't want to deal with that. So it's one of those things where if you know what you're talking about and you're intentional in the words that you're using, you can open opportunities once you're in the clinical setting that you otherwise will not get. Make sense? All right, do we have any other questions online at this point? Doesn't look like it. Okay. What else are we looking at? Yes?
So you talked about memorizing the mechanisms of drug action, and the first one on the slide, you want us to remember, I was looking at it and it talks about the site of action at 50S subunit,
For tetracyclines?
I don't know. Is that for protein synthesis inhibitors?
Oh, the very first slide.
Yeah.
Okay, yes. So for the first slide, I want you to know the different modes of action. All right. So if you take an antibiotic, the antibiotic's either going to, one, interfere with the ribosome, either the 50S subunit or 30S subunit. It's going to inhibit metabolism. It's going to inhibit cell wall synthesis. It's going to potentially inhibit plasma membrane synthesis or structure, or it's going to inhibit something with the genome, DNA or RNA, or metabolism. All right, so I want you to know what are the major categories in terms of what do antibiotics block, right? Because each antibiotic will have a specific mode of action. All I wanted you to memorize out of each one of those categories was the first antibiotic. So if I say, you know, penicillin, since we spend so much time talking about penicillin, I want you to be able to go, oh, penicillins, yes, those are definitely cell wall inhibitors, right? But I don't want you to memorize the 5 or 6 that are on the list, just the first one in each category on that first slide. That's enough. It's a good starting point. Does that make sense?
Yeah.
Good. Yes.
Do you want like the steps of the complex capsid, like how it actually injects into?
Oh, yeah. All right. So the question was if I could walk through the steps of the complex capsid. So complex capsids, the example that when you're talking about complex capsids, are you talking about bacteriophages? Right? Bacteriophages, or phages as they're often abbreviated, they look a lot, people often describe them as spiders. They say that they look like spiders. And so this is my terrible drawing of a phage or a complex capsid. But what happens here is that, again, these infect bacteria, and they have these kind of legs, right? And the legs are literally just like a landing pod. So the phage will come and it will land on the surface of the bacteria. Once it lands on the surface of the bacteria, the phage literally will crouch or sit down. And that's where that spider analogy comes in handy. Because, you know, if you scare a spider, it'll literally kind of crouch down a little bit. The phage molecule does the same thing. And what happens is when it crouches down, there's a variety of these teeth. I believe your book references them as tail pins, but they look just like teeth, where they will literally puncture. So if this is the surface of the bacteria, this whole thing crouches down, and those teeth inject themselves or puncture into the surface. So let me just redraw the legs here. So let's imagine that this whole thing crouched down, and that's the surface of the membrane, and the legs are just like this now. So it has literally punctured that cell wall of the bacteria. And it has a variety of enzymes, like lysozyme, that it will bore a hole into the cell wall. Alright? After it bores that hole into the cell wall, it's like a tube, more or less. And after it's done boring, this part here that I drew these lines is like an accordion. It's called the sheath. The sheath contracts. Alright, and that molecular mechanism of the sheath contracting causes the genome inside to travel through the tube and be injected into the cell that it's infecting, the bacteria that it's infecting. Alright, so it's this mechanism of crouching down, dissolving a hole into the cell wall, and injecting the genome, whether it's DNA or RNA. Now, phages are they're all over the place, right? You know how we develop antibiotics? The Russians and the Soviet Union, their big program was they said, well, there's always these phages around, right? There's this whole form of virus that all it does is infect bacteria. Why don't we create antibiotics that are just phage viruses? You know, viruses that go into bacteria and blow them up. You know, why don't we do that? That sounds kind of smart, right? When you first hear it, you're like, wow, that's a great idea. And they developed that program for a good number of years until they discovered that just like we have antibiotic resistance, there's also phage resistance. Bacteria can develop a variety of mechanisms that we didn't talk about in class to become phage resistant. And phage resistance actually happens faster than antibiotic resistance. And so that's why you don't hear of these phage programs, because the Soviet Union tried it and it failed miserably. But in nature, these infections happen all the time of bacteria specifically. So when you see a complex capsid, you're talking about a virus that infects bacteria. Good? Awesome. right. Do we have any questions online? All right, we haven't had any since I checked last time. What else do we have from you?
Static, silent, agent, static.
Yeah, so anytime you take a cytal, like antibiotics are the same way, right? If you take a bactericidal antibiotic, let's say this is a graph of number of bacteria, so we'll put concentration of B for bacteria, and this is change in time. Let's say you get sick, you got a lot of bacteria, and you take a bacteria cytal antibiotic, right? You're going to kill that bacteria, and you cleared the bacteria, so your symptoms are going to go away, right? If you have that same infection take place, but instead of taking a cytal antibiotic, you take a bacteriostatic antibiotic, what will happen is that you'll still get bacteria production, but when you get on the antibiotic, you're basically just level off and preventing further growth. And you'll notice over time the amount of bacteria decrease because that's your immune system attacking the infection. Right? You're suppressing the bacteria from further dividing or making more copies of itself without necessarily wiping it out. Because again, wiping out a complete subset of your bacteria is very dangerous. The example I always use is E. coli. Right? If I have an E. coli infection in my arm and I take a bactericidal antibiotic that kills all E. coli in my body, you are in for some really rough GI consequences. Right? And so often they'll put you on a bacteriostatic antibiotic so you don't get further growth at the site of infection, but you don't wipe out what's in your GI tract, and then subsequently your immune system can clear that infection. They're pretty effective. Even if you are put on, let's say, for example, my son, remember how I got that lung infection like a month ago, month and a half ago, and I could barely talk? My son got that from me, and he is now on antibiotics for the next 2 weeks. They also put him on a probiotic because they know the antibiotic that they're putting on is wiping out a good chunk of his commensal bacteria. And instead of having an upset stomach and having maybe diarrhea, they give him a probiotic to regain those bacteria that he's losing in his GI tract because of the antibiotic. So it's always a balancing question.
I was going to ask you about probiotics actually, but
Yes.
in relation to that, is like yogurt basically probiotic?
Yeah. It's later in the semester. It's one of my funny.
Is that one of the foods you do?
No, it's not one of the foods I ruined for you. It just cracks me up. You'll hear it again later in the semester, but you're here now, so you can hear a funny story. Like if you go next time you go buy a yogurt, like an Activia is ridiculous for this. If you read the back of an Activia jar, it says there are active cultures of Bifidus regularis.
I think they all say that.
Yeah.
Active cultures. Live.
Yeah, live cultures, but Activia in particular says Bifidus regularis. Have you ever heard of the bacteria Bifidus regularis before? Does Bifidus sound like anything? Regularis sound like regular, very good. So what they did is they took a bacteria strain used for making yogurt, and they did a single mutation in it in something that didn't matter. And so they could patent it and rename it whatever they wanted. And they said, well, Bifidus, okay, but regularis, people are going to say, oh, if I drink or eat yogurt, I'll be more regular because there's Bifidus regularis in it. That's corporate America.
It sounds like an absurd name anyway.
It is an absurd name because it's completely made up for patents.
That actually cracks me up.
Yes, it cracks me up.
Marketing at their finest.
That is an amazing marketing. But yes, your Bifidus regularis is a corporate marketing. But yes, but does yogurt work as a probiotic? Yes. Are there a variety of probiotics that work really well? Yes. Culturelle is an example of one. You can go to the pharmacy and look. But if you are on extended antibiotics, your doctor should put you on a counteractive probiotic so you're not destroying your GI tract. We'll talk about it later in the semester too, there are actually infections that you can get where if you wipe out your GI bacteria, that you can get a secondary infection that can cause actually pretty serious pathology. But we'll talk about that more later in the semester. Good questions. See, you never knew you could have so much fun in microbiology. Okay, so we've talked a little bit about viruses, we've talked a little bit about control, we've talked a little bit about antibiotics. So what else is still popping out on the page is confusing, or you're not quite sure how something works.
Is there a big subject you think we're missing that we're not asking about?
I think as long as you, I'm getting chalk everywhere. As long as you really, the area that people struggle on this exam the most is one, understanding what a virus is, what is it made up of, and what are the steps that it takes to reproduce or make copies of itself. People tend to struggle with that a lot. In terms of antibiotics, people struggle with knowing what are the broad spectrum versus the narrow spectrum antibiotics. I will ask you questions like that because I want you to know if I'm on a polymyxin, is that a broad spectrum or a narrow spectrum antibiotic? If I'm on a tetracycline, is that a broad spectrum or a narrow spectrum antibiotic? I want you to have just a very general understanding of that. That's areas that people struggle on. In terms of the cleaning or the microbial control of infection, people generally just don't study the definitions enough. If you look at the bottom corner of the first slide on Blackboard, you have that first slide that shows disinfection and it shows you all those pathways. That bottom right-hand corner of the slide has the definitions right now on one little square there. Go read it. It helps. But overall, this one just has a lot more in terms of terminology. It's a little bit more difficult concepts to think about. And for many people, it's their first true exposure to viruses. Antibiotics do not work on viruses. Let me say that again. Antibiotics do not work.
True or false?
You're going to hear this the rest of your life. People are going to come to the clinic and they're going to be sick and they want an antibiotic. And they're going to huff and puff and fuss because they want medicine. They want a paper. They want to take a pill to feel better. And 90% of the time, if you have a viral infection, what do? Supportive care. Rest, water, sleep, take it easy. But supportive care. And people struggle with that.
I think we should just give them like placebo water pills.
Yeah.
Yeah.
Yeah, there you go.
Something's got to change. Most of it comes down to, honestly, it's you guys. You are the front line when it comes to patients in the hospital. I can tell you the last 5 times plus that I've been in a hospital, it's not like private practice or ER or Grey's Anatomy or whatever, Chicago Med, where you watch a TV show and there's 15 surgeons on the floor. That's not how it works. There's nurses, there's patient care technicians. Those are the people interacting with the patients. You know, and I could tell you when my son was born, when Benjamin was born, every single nurse, every single PA, every single person except for the delivery nurse and the doctor, the MD, was a St. Francis alumni. 100%. The floor nurses, the charge nurses, people in the room, people outside the room, all St. Francis credits. So that's why I care, because you guys are going to be the ones with the opportunity to educate the patients. Oh, I just want an antibiotic. This is why that would be a bad idea. First off, it's not going to work. Second off, it's going to promote resistance. And we're having major issues with antibiotic resistance. And you don't have to tell them, and I know you're not going to take your pills right anyway. Right? So we talked about that a little bit today in class, how patient compliance is terrible.
Yeah.
And And so you want to take that as a clinician. Your job isn't to rag on patients, but your job is to educate. You have the chance, you have the power. You know, I'm one person, you're a lot of people. You guys have the opportunity to make a difference in the clinical setting. So educate them, spend 5 minutes teaching them on why the antibiotic won't help their virus. And the world will get better. But it's going to take some effort. And try not to roll your eyes, try to be compassionate. They don't have the education that you have, and that's why you're sharing. Amen. What else do we got? You haven't gone over that.
Okay.
That's tomorrow. So we'll go over HMRSA and HMRSA and what does that mean clinically.
I have two things. One, so DNA and RNA, it's one or the other in the virus?
Yeah, or.
Or.
Yeah, keyword there is or. You never have both. You either have a DNA virus or an RNA virus. And remember, the RNA viruses were the fast-acting ones. Those are the ones that you get the virus infection in the morning and you're puking your guts out by noon. Whereas the DNA viruses are the ones that tend to last a long time, sometimes even a lifetime. Those are the infections you can't get rid of. Something we haven't talked about with viruses also is host range. Remember, we had broad host range, narrow host range. That had to deal a lot with what tissues are the viruses infecting. But remember, the glycoprotein interacts with a specific receptor on that host cell, and that has to be an exact fit. Otherwise, the virus will not infect that cell.
And then the other one, can you briefly go over broad spectrum versus narrow spectrum?
Yes. So when I say something is a broad spectrum antibiotic, that means it is an antibiotic that has a mechanism that allows it to act on many different types of microbes. The classic example is that broad-spectrum antibiotics, for example, can generally work on gram-negative or gram-positive infections. Some of them can work on different classes of bacteria, but it's a lot. It's not just E. coli. It's not just Staph aureus. When you talk about a narrow-spectrum antibiotics are given for specific infections. Okay, they only work on gram-negatives, or they only work on gram-positives, or they only work on your spirochetal infections. They have a very specific mode of action, but they're very, very effective at treating those infections. The problem you run into is when somebody gives you an antibiotic that's really good for gram-negative infections for a gram-positive infection, because it won't work, and you might as well not be taking anything. So broad spectrums, a wide range of classes of microbes they can work with, whereas a narrow spectrum is only going to focus on, a genre or a few genre of bacteria. So that broad spectrum antibiotics, somebody comes in the room, they have an infection, right? They have some kind of a surgical wound, and it's pussing, it's inflamed, it's red, it's yellow. You can clearly tell that they have an infection, but you have no clue what it is. You're going to immediately put them on a broad spectrum antibiotic while you wait for the lab tests to come back and say, this is Staph aureus or this is E. coli. Once you know what it is, you can give them more specific antibiotics, but you want to give them a broad spectrum antibiotic that says, I don't know what it is other than I know it's a bacteria. You give them that broad spectrum antibiotic to just get things managed or under control. Then you can specialize it once you have a better idea of what infection they have.
You have to wait a certain amount of time before you do that.
No, you can switch them from one to the other. There's no problems with that.
Are there like different clinical manifestations of like bacterial infections, viral infections, and how do you know?
Correct. Yeah. So the question was, are there different? Yeah. So the question for the internet people is there a big difference between like bacterial infections and viral infections clinically that you would tell, should I give them an antibiotic or not? And the answer is yes. So they can range everything from basic presentation. So basic presentation can be something as, my patient has come in and they're hacking up a lung, coughing a lot, okay? At that point, they're either viral or bacteria. But what color mucus are they coughing up? If they're coughing up mucus that is yellow or green or red, because they're bleeding a little bit, but especially like yellows and greens, sometimes browns, that means they have a bacterial infection. That yellow is actual bacteria in the mucus that they are coughing. Okay? If you have a viral infection, you can be coughing your lungs up constantly, and more or less your mucus is going to be clear. Right? A very clear, productive cough. That's virus. So that's a real quick gimme right away if you're talking about a respiratory infection. If you do blood work, bacterial infections, you're going to see huge spikes in neutrophils and band cells, white blood cells, whereas in viral infections, you don't always see that huge uptick in immune cells, in terms of innate immune cells. And so that's another example. Flu virus, for example. Do you have influenza? Influenza you do not produce a productive cough. You're coughing like you're almost choking on something, but you're not producing any saliva, sputum, mucus, whatever you want to call it. The reason that you're not producing anything actually has to deal with the flu itself. You know, one of the products of the flu is an enzyme called neuraminidase. So influenza virus produces neuraminidase. Neuraminidase shuts down your goblet cells in your trachea. You shut down the goblet cells in the trachea, you can't produce mucus. Now, why would a virus do that? Why would it shut down goblet cells in the trachea? Yeah, because if you're producing mucus, that virus can get stuck in the mucus and you can cough it up. But that virus wants to get to the epithelial cells in your respiratory tract to cause an infection. So it shuts it down.
But like overall,
you can do lab tests, right? You can take a clinical sample and you can plate it out, right? Very easy to do. Another thing that you can do is there are a variety of rapid tests where you can take a clinical sample and within an hour you can know with almost 100% efficiency what bacteria does that person have, or do they have a viral infection, yes or no. So our tools are getting much better. It really just depends on what person's coming in with, right? If the person comes in with a common cold, like rhinovirus, you don't want to sit there and do a bunch of lab work on it because it's the common cold. They're not going to die. Knowing which virus they have, which form of rhinovirus they have, doesn't matter because rhinovirus infections only last 7 to 10 days. And there's nothing you can do for it. You just supportive care. So you're not going to charge them the hundreds of dollars to run the lab test if it's something they're going to get better with on their own. They'll just do supportive care. But yes, there are a variety of different tests. There are a variety of different clinical presentations that lend towards what type of an infection they have.
I was just wondering, so if I'm looking at I feel like I just like saw those medicines and I get antibiotics. So I just wonder how they would decide for that.
It depends on the clinician. It depends, are you going to like a family doctor that's seen lots of cases? Are you going to a hospital? Are you going to an urgent care facility? Different places have different protocols for how they prescribe stuff. Good question. All right, anything else? Awesome. Well, I think we're good to go.
Thank you.
No problem at all. That wraps up the online session, and we will